Swayam Prabha. Digital India. Educated India.
So, let us come to the 37th lecture on cryogenic engineering under the NPTEL program. The earlier lecture we were talking about vacuum, and during the earlier lecture we talked about heat inleak is minimized by having vacuum between two surfaces of different temperatures. Then we talked about lambda, which is mean free path of the molecule, and lambda is defined as the average distance travelled by the molecules between the subsequent collisions. And we had seen that based on this lambda, we had classified the different vacuum levels. So, based on the Knudsen number, again we have got a number analogous to Reynolds number in the continuum flow. We had Knudsen number which is equal to lambda by d, where d is the characteristic dimension. And based on Knudsen number Nkn, we had continuum flow when the Knudsen number is less than 0.01. We have a mixed flow when the Knudsen number is between 0.01 and 0.3. And we got a free molecular flow when Knudsen number is more than 0.3. All right. So, normally in very good vacuum, we will always encounter a situation when we got a free molecular flow. And we also studied what is this conductance, and when we found that conductance will depend on the length of the pipe, diameter of the pipe, the gas, the temperature, the pressure, etc. We have got conductances in series. That means we got a pipes in series. The conductances would get added like this. So, 1 upon C0 is the overall conductance of the entire pipe structure, which will depend on as sigma 1 by Ci, where I will go from 1 to 2 or 1 to 3 depending on how many pipes you have. So, 1 upon C1 plus 1 upon C2 plus 1 upon C3 is equal to 1 upon C0, and in that way we can calculate overall conductance. Similarly, if you have got pipes in parallel, the conductances will be added. C0 is equal to sigma Ci, they will be directly added to each other, and they will, with that we will get an overall conductance for the parallel pipes. And this will be utilized ultimately in order to get the vacuum speed, the pumping speed, and that is what we will see in this particular lecture. So, in this lecture now we will continue with what this conductance business is all about. Then we will come to very important parameters quite regularly used in vacuum technology, which is pumping speed and pump down time. All right. So, we will come across what is these terminologies which are normally used in vacuum technology, and then we will have some tutorial based on this pumping speed, conductances, pump down time, etc. And therefore, all these things which we are understanding in this particular lecture, we will have some tutorial based on it, and we can have some values associated with all these parameters. All right. In the earlier lecture, we have seen the importance of vacuum in cryogenics. We have seen the mean free path lambda and the degree of vacuum will decide the fluid flow regime. All right. And then we had Knudsen number also in order to classify these different flow regimes. The conductance for circular pipe for continuum, mixed and free molecular flow regimes respectively were derived as shown below. If you remember the derivation which we did last time, we found that conductance for continuum flow is proportional to d to the power 4, and this is what the expression we had got at Poiseuille equations basically. Then for a mixed flow, we had a conductance which is typically a little mixed behavior, and you got a very not direct relationship between the diameter over here, but it is inversely proportional to the length one can see, and diameter d to the power 4 is here in the numerator, while d is there in the denominator also. And when we come for a free molecular regime, the conductance is now proportional to d cube and inversely proportional to L. So, these are the conductances which we found that they vary with different diameters, they vary with lengths, they vary with pressures, they vary with temperatures, and of course, the gas property like viscosity, etc. So, using this formula, depending on the flow regimes you are in, we will have to calculate for a given pipe of a given diameter and length, what is the conductance of that pipe, and this will determine, ultimately help us determining what is my pumping speed or what is my system pumping speed, etc. And this is what we will see in this particular lecture. So, conductance is a vacuum. As mentioned in the earlier lecture, vacuum systems involve complex piping arrangements. These piping arrangements may involve circular straight tubes rectangular straight tubes, 90% elbow joints, etc. and actually lot of other structures which has not been mentioned over here. We can have some couplings also involved over here. We can have some bends over there. They may not be 90% again, all right. So, in order to calculate the conductances for such mechanism, because I got a vacuum pump, I got a system to be vacuumed, and in between I will have some piping arrangements, all right. So, vacuum pump cannot directly go and sit on the system. The vacuum pump is going to be away from the system to be vacuumed, and therefore, these piping arrangements effectively will determine what is the conductance which is responsible to get particular system pumping speed. So, if I got some structures which are circular straight tubes, rectangular straight tubes or 90% elbow joints and many other possibilities, but I am just showing you 3 possibilities, then there are some standard equations to be used in order to calculate the conductances for these particular pipes, joints, etc. The table on the next slide gives the conductance equations for some commonly used pipes and pipe joints, and we have to use such correlations that are available to calculate the conductance in order to come to calculate overall conductance of the system. For example, we got a long tube, and long tube is defined as when L by D is more than 30. So, L is length, D is diameter, and for a continuum flow we have got a relationship as we have derived earlier as pi d to the power 4 p 125. So, use this equation to calculate conductance if we are in continuum region, or if we could prove that we are in free molecular region, then use this formula which we have ultimately derived. All right. So, use such formula. First find out what is the Knudsen number, ensure that you are in a free molecular region, mixed region or a continuum region, and use corresponding formula to calculate the conductance for that pipe for a given dimensions T, D and L. If you got a short tube where L by D is less than 30, then again we have got different formula, and if you got a free molecular region, we have got a different formula again, where D1 and D2, we can have 2 joints, 2 diameters also, having D1 as large and D2 as smaller diameter. So, use all these things in order to calculate the conductances for such given pipes. If you got a 90% elbow, which may look like this, you can see that the gas flow in this direction, and you can see there is a radius of curvature and this is the diameter of the pipe, and again we have got expressions for calculating the conductance for a continuum flow for a free molecular region, and the value of K which is showing up here over here depends on particular R by D. This is basically is shown up only in this only. All right. So, find out that, calculate the value of conductances accordingly and put those values here, and for different structures, therefore, for different pipes, for different joints, for different curved elbows, etc., you calculate the conductance in this way, and then effectively you will calculate if there are pipes in parallel, if there are pipe in series, one can calculate the overall conductance of this combination of pipes. In addition to this, we will have several couplings. We can have several non-characterized kind of items which could be placed in place, or pipe of different structures also could be placed, and then correspondingly you will have a very big table that is available in literature, which you have to look for, and you can get the conductances for those particular structures which are employed to connect vacuum pump to the system to be vacuumed. Now, let us come to know what is this pumping speed. So, what you can see here is a cavity or a cylinder which is shown to be vacuumed, and there is a vacuum pump kept on the right. The vacuum pump is a known device to me, and therefore, vacuum pump will have its known characteristics. However, this vacuum pump is directly not mounted on the system to be vacuumed, but it is connected to some piping arrangement, and therefore, the conductances of this pipe also becomes very important. So, consider a closed cavity and a vacuum pump system. So, closed cavity, vacuum pump and connections given by pipes over here. This pipe can have different diameters, different elbows, different joints, and corresponding to that we will have a different overall conductance for this pipe. So, you can see a closed cavity vacuum pump system as shown in this figure. For the above system, let us assume the following parameters. Pi is the pressure at the inlet to the vacuum system, which is Pi at this point. P is the pressure in the cavity. So, this P and this Pi will be different. The vacuum at this level will be very high because I got a vacuum pump here. So, the pressure at this point will be less, while the pressure at this point will be little bit more, and how much more will depend on the conductance of this. All right. So, we know that we can suck the gas molecule from this only when that the pressure at this point is going to be less than the pressure at this point, and therefore, this vacuum will have a different pressure Pi, while this system to be vacuum or the cavity to be vacuum will have pressure little bit higher than what you get at the vacuum pump. Q is the throughput of the pump. So many bar liter per minute or pressure into liter per minute, what is the unit of throughput of the pumps, which will be known to you. And the CO is the overall conductance of the piping. So, depending on the pipes that have been used, the couplings that have been used, the elbows that have been used will have some overall conductance of this pipe. In order to analyze the above system, the following quantities are defined. And what are those quantities? The capacity of a vacuum pump is denoted in terms of pump speed. So, we got a pumping speed SP, and this is known to me because the capacity of vacuum pump, when I buy a particular pump, I should know what is its capacity. So, how many meter cube per minute, meter cube per hour, liter per minute, liter per hour that this particular vacuum pump can suck, all right. And again this capacity normally is given in for a particular gas, let us say nitrogen, normally it is defined as. So, every vacuum pump when you buy, it will have its capacities defined, all right. So, a pump speed is normally defined for a given vacuum pump. So, what do we define this pump speed as? It is the ratio of the throughput Q to the pressure at the inlet to the vacuum pump, all right. So, Q upon Pi, and therefore, we can see mathematically SP is equal to Q upon Pi. So, whatever throughput it is basically getting, right, pressure into volumetric flow rate divided by Pi at this particular point, we will get that as a throughput divided by Pi is going to be my pumping speed, and the unit of this will be like volumetric flow rate, meter cube per second, it could be liter per minute, liter per hour, depending on the kind of pump we have been talking about. So, pumping speed, as we said, is a standard for a given pump. Depending on the pumping speed, my cost of the vacuum pump also will increase or decrease. So, SP is equal to Q upon Pi. Pi is the pressure at the vacuum pump. On the similar line, there is a system pumping speed. So, we got a vacuum pumping speed, which is a pumping speed normally referred to as, and then we have a system pumping speed, which is specified for the system here. All right, this is my system to be vacuum. This is my vacuum pump I have been utilized, and this is the way I have connected this vacuum pump to the system. All right. So, on the similar line, system pumping speed SS is defined as a ratio of throughput Q to pressure in the cavity or the vacuum. Now, I am talking vacuum space, that is I am talking about the pressure of the system. So, this pressure, as I said, is going to be more than pressure what you see at a vacuum pump. So, system, ultimately what is important for me is what is my system pumping speed, because I am interested in vacuuming in this particular cavity. To get this vacuum over here, I am using this pump. But if I use a different connections as given over here, my system pumping speed is going to be much different than what my vacuum pumping speed will be. All right, and let us see how they are related basically. So, mathematically we see that SS, which is my system pumping speed, is equal to Q upon P. So, Q is the throughput, but the P is now the pressure of the system over here. All right. So, this pressure is going to be little bit more as compared to what you get Pi at this point. So, definitely what you understand from here, SS is going to be less than SP. So, system pumping speed is going to be less than the vacuum pump speed or the pump speed. Again, the units are meter cube per second, liter per minute, or whatever units you want to use. The conductance now, everything depends what is the value of SS depending on the value of SP, but SP, the pump is connected through the system to be vacuum through a conductance. All right. So, I can have a very large vacuum pump, but I can connect it through a very small tube, and therefore, the conductance in this case is going to be very, very small, and therefore, that will affect the system pumping speed. So, the conductance is given by Q upon P minus Pi, which is what we have seen earlier. So, what is the difference of pressure across this piping, P minus Pi? This will determine what is my conductance. As you know, P is more than Pi. And this is again unit will be conductance unit will be same as pumping speed. So, we know now SP is equal to Q upon Pi, SS is equal to Q upon P, and C0 is equal to Q upon P minus Pi. So, now got a relationship between P, Pi, P minus Pi. And how are these related? How are these pressures related? Pi is equal to now Q upon SP, P is equal to Q upon SS, and P minus Pi is equal to Q upon C0, Q upon overall conductance. So, if I put these values of P and Pi over here, I will get a relation which is connecting now C0, SS and SP. I get connection between pumping speed, system pumping speeds and overall conductance. So, if I did that, eliminating the pressures Pi and P from the above equations, what we get therefore is Q upon SS is equal to Q upon SP, and transposing it a little bit, I will get Q upon SS is equal to Q upon SP plus Q upon C0, and I can eliminate Q from these equations, and what you get ultimately is 1 upon SS is equal to 1 upon SP plus 1 upon C0. Now, this is a very important relationship which connects system pumping speed to the pump speed to the conductance of the pipe which is going to be connecting my pump to the system. So, it depends on what is my pumping speed and what is my conductance. These two will determine together what is my system pumping speed, and therefore, this is a very important relationship to decide if I want to design a particular system, vacuum system, to get a particular SS, I will have to worry about both these parameters SP as well as C0. And let us see how do they show up. So, this is my relationship 1 upon SS is equal to 1 upon SP plus 1 upon C0. From the above equation, it is clear that SS is lower than the minimum of SP and C0. This is a simple mathematical thing. You got a reciprocal rule, SS, which is the resultant of SP and CO, is going to be less than the lowest of these two. So, if SP out of SP or C0, whoever is lower than that value will be the value of SS. Normally, I would like to be SS to be very, very high, but you have to understand that SS cannot be more than the low, I mean it will basically be depending on what is the lowest of these two, all right. So, SP depends on vacuum pump. Let us understand now what is the parameter which that dominates the value of SS. So, SP is a vacuum pump which I have bought, and therefore, I know everything about SP. I know that so many liters per minute or so many meter cube per second is what my pumping speeds of a available pump is all about. So, SP depends on a vacuum pump, and therefore, in order to maximize SS, if I want to maximize SS, I have to maximize my CO. So, if I increase my CO, I can have SS coming closer to the minimum of SP and CO. In principle, what could be the maximum value of SS? The maximum volume of SS could be SP provided CO is infinite. If CO is infinite, 1 by infinity becomes equal to 0, and we can say that 1 upon SS is equal to 1 upon SP. In that case, we can say that the maximum value of system speed is going to be can be equal to the pumping speed. So, in principle, SS can maximum be equal to SP, and SS can maximum when CO is infinite. So, when CO is infinite, what we get is this. If CO is infinite, then we have SS is equal to SP. Can we have CO as infinite? Is it possible? We will see that later. For a given connecting pipe now, conductances increase with decrease in length and increase in diameter. So, can I make my diameter infinite or length to be equal to 0? Then only my CO is going to be infinite. So, in principle, I cannot do. So, what I can do? I want to increase my diameter as much as possible, and I want to decrease my length connecting vacuum pump to the system to be vacuum to a minimum distance. So, keep minimum length of a pump away from the system to be vacuum and keep maximum diameter of the connecting pipe, so that the conductance is going to be higher in that case, and therefore, SS can go as high as possible. But as you understood, SS can maximum be equal to SP and not more than that. So, let us try to go as close as much to the value of SP, but everything then depends on what is my conductance. Similarly, if CO is equal to SP, let us say in a case, just an extreme case, if CO is equal to SP, then my SS is going to be half of SP. So, you can see that if CO is equal to SP, then we have SS is equal to SP by 2. So, go on increasing conductance as much as you can, so that this parameter become very small. In that case, my SS will approach to SP value, and that is what we want to ultimately achieve. So, my system pumping speed should approach the vacuum pump speed. Now, having understood what is system pumping speed, what is pump speed, or what is conductance, all these things having understood, let us now come to what is pump down time. So, consider a closed system as shown in the figure. This is my high pressure to begin with. let the initial pressure in the system be Pi. Before I start vacuuming, my pressure is going to be initial pressure, which is Pi, and after vacuuming I reach a final pressure which is Pf. So, I can see that less number of molecules over here, and this is my completely low pressure which I have got after vacuuming from Pi to Pf. So, when I connect my vacuum pump to this unit, ultimately I reach the value of Pf, and this time it will require a lot of time. Basically, it will start sucking the molecules, and how much time it takes to reach a value Pf will depend on the conductance I have used, the vacuum pump I have used, and all those parameters will come into picture. So, the amount of time taken by a vacuum pump to reduce the pressure from Pi to Pf is called the pump down time. So, it will depend on all the parameters. It will depend on the vacuum pump, it will depend on the conductance I have used to connect this vacuum pump to the system to be vacuum. So, all these parameters will determine what is my pump down time, and this pump down time is a very important criteria, because if I want to do an experiment which will last for only 2 hours, and in one day I would like to do this experiment 2 or 3 times, my pump down time should not be more than 2 or 3 hours. I should get a vacuum within half an hour or 10 to 15 minutes, and therefore, I have to design my vacuum system in such a way that I should get my vacuum Pf, what is my pressure Pf, within 10 to 15 minutes or half an hour or something like that. Alright, so this is very important, and it depends on what is my Pf I am talking about, what is my conductance, how do I connect that conductance to the vacuum pump, and all those parameters will determine what is my pump down time. So, application decides the degree of vacuum. If I want to decide a particular experiment, that experiment will decide what degree of vacuum do I require, what is my Pf requirement, what I want -5 torr, -6 torr, -3 torr vacuum levels, and this is what we call as degree of vacuum. So, decide first what is that lowest pressure I want, what is vacuum I want, what is degree of vacuum I want. Depending on the application, the required pump down time is determined. So, according to that, I will decide what is my pump down time. Should I have 15 minutes, 20 minutes, half an hour, 2 hour, 5 hour, complete day. Alright, it depends on application. It depends on how big my system is also, because bigger the system, bigger time it is going to take to pump down all the molecules. Alright. So, pump down time helps in selection of vacuum pump. So, I have to decide what is my volume to be sucked, what is my volume to be vacuumed. According to that, I will decide what my conductance should be and what my pump should be. So, ultimately, depending on my application, depending on my pump down time, I will decide the vacuum pump to be employed for this purpose. So, the vacuum pump is, the pump down time is a very important criteria to decide a vacuum system. Hence, there is a need to study the pump down time of vacuum system. So, can I calculate this pump down time? And that is why we are coming over here. So, if I know pump down time, can I select a particular vacuum system or a vacuum pump for a given operation? And therefore, this parameter pump down time is a very important parameter. Now, this parameter will also depends on what are the leakages paths. The gas is going to get leaked over a period of time, and the gas is going to get leakage paths could be definitely there. As long as the fabrication happens, you got always joints, you got some seal matters, you got a material which outgasses, and therefore, gas leak is always going to be there. So, apart from heat in leak, gas in leak and outgassing are the major problems posed by a cryogenic system. Alright. So, there is during fabrication some gas has gone into the material, and this will outgas over a period of time. This will come out over a period of time, and therefore, there will be constant gas in leak in the system, and this has to be taken care by the vacuum pump. These leakage paths have to be considered for calculation of pump down time and selection of a pump. So, I should know what are these leakage paths and what is the leakage quantity also, what are the flow rates also I should know. The leakage paths increase the pump down. More the leakage path, it will take more time to reach a required vacuum for a particular application. So, I should know all these leakage paths, and I should know all these quantities that are leaking, and what are the gases also, I should have an estimate for those things also. Alright. So, gas enter the system due to actual leak through the vessel wall joint. So, this should be minimized actually, So, you got a weld, it will have some leak however, and that whatever that leak is, it has to be considered. So, actual leak through the vessel walls and joints. Suppose you got a joint which is a mechanical joint, or which has got a seal across, O-ring across it, then it will start leaking over a period of time. It will have some its leak rate associated with that thing. That also has to be considered while calculating the pump down time. Then the trapped gas release from the pockets within the system, also called as virtual leaks. So, there are material surface is there, and there are some trapped gases inside this material. It will get released once you start vacuuming. that also has to be estimated. See, this parameter become very important if you want to go down to -8, -9 kind of vacuums. All right. So, these are very important to be considered while calculating pump down time. Outgassing of the metal walls or seals, and this is what you just talked about. All the non-metals, all the metals in a system will start outgassing, and we got some outgassing quantities in available table also for vacuum technology. So, one should know what are these outgassing rates for a given material, for a given seal, etc. All these have to be considered in order to consider gas leaks, and in return it will be basically taken into consideration to calculate the pump down time. Outgassing is the release of adsorbed gases either from surface or interior or both when exposed to vacuum. All right, this is a very slow process. Outgassing happens over a period of time, over 6 months time, over a 1 year time, and it all depends on what fabrication the material has gone through, and therefore all these things have to be understood when we start designing for a particular application of vacuuming, and especially where vacuum is plays a very important and crucial role. The major contribution to the mass in leak is the outgassing. So, out of all these parameters, the outgassing is a very important parameter that has to be considered. The contribution from outgassing is going to be a major contribution to mass in leak, and that's why it has to be considered correctly while designing a particular vacuum system. So, now let us understand how do I derive an expression for calculating pump down time. So, let us see this system. So, consider the closed cavity as shown over here with a vacuum pump system. So, you got a entire thing will be a vacuum pump system, a closed cavity connected to a vacuum pump through a given conductance. All right. So, consider a closed cavity vacuum pump system as shown above, and we got two parameters. Let the mass flow rate leaving the system is m dot out, which is coming from over here, and this is my system to be vacuumed. This is my piping which has got its conductance, overall conductance as C0. The throughput could be called as Q from here, and this is my PI, which is the pressure at the vacuum pump or the vacuum level basically at the vacuum pump. So, mathematically I will say m dot out is equal to rho into SS. What is my SS? SS is the system pumping speed. So, depending on SS, I got some meter cube per second, multiplied it by kg per meter cube, and therefore, what you get is a mass flow rate which is leaving the system, which is m dot out in, let us say, kg per second, kg per hour, whatever. So, m dot out is equal to density of the gas into SS, all right, where rho and SS are the density and the system pumping speed respectively. Please understand this clearly. Now, similarly, I will have some m dot I, and let the total inflow due to gas leak and outgassing be m dot I. It can also be written as m dot I is equal to Qi divided by RT. So, depending on heat in leak now, depending on the gas in leak in a system. So, you got several joints, we got several outgassing possibilities, and depending on all these seal materials used, etc., we will have some Qi, and therefore, as a result of which we will have some m dot I, all right, and this could be again a constant, or it could be a question of time, it could be dependent on time, all right. So, it can change with time also. So, let the total inflow due to gas in leak and outgassing be m dot I. It can also be written therefore as m dot I is equal to Qi upon RT. Now, applying the mass conservation to this system. So, I am talking about system only the cavity to be vacuumed right now, where m dot I is mass in leak and m dot out is mass which is going out of the system. So, we have m dot I minus m dot O is equal to dm by dt, and this is a very standard expression for law of conservation of mass basically. From the definition of density, we have m is equal to rho into V. This is my volume, and therefore, m is equal to rho into V, and therefore, m dot I minus m dot out is equal to V into d rho by dt. So, if I write dm by dt, basically I can write dm by dt in terms of d rho by dt multiplied by volume, all right. So, now I got expression which is talking about d rho by dt, and therefore, can I relate it to dp by dt now? Yes, I can. So, m dot I minus m dot out is equal to V into d rho by dt, which is a change of density with time. Using the ideal gas law now, what we have is equal to PV is equal to RT. So, we got a P is equal to rho RT, and therefore, now I got an expression for rho in terms of P and RT, where RT could be considered to be the constants, and therefore, now expression changes, and I get an expression which is talking about now dP by dt, which is a pressure change with time, and this is what we are aiming at basically when we are trying to vacuum this system out basically. So, m dot I minus m dot out is equal to V upon RT, RT being constant is coming out of this, and what we get is the dP by dt. We get expression for dP by dt now. So, combining the following equations now, we know that m dot I is equal to Qi upon RT. We know m dot out is equal to rho into SS. This is what we have seen earlier. Put those values over here. What we get therefore is equal to Qi upon RT minus, replacing this rho as P upon RT, what we have got here, we get P upon RT into SS, that is PS upon RT is equal to V upon RT dP by dt, and therefore, all the RTs would get cancelled, and what you get ultimately is dP by dt is equal to Qi upon V minus SS into P upon V. So, you got an expression now which depends on the system pumping speed, the pressure, the volume to be vacuumed, and the Qi, which is talking about basically the mass in leak throughput. So, I got expression like this now, and if I want to now calculate the time to get a pressure from P1 to P2, I can basically integrate this, and this is what I will do some mathematical treatment on this. This equation is valid for any vacuum system in general. For any vacuum system now which has got mass leak as given by Qi, we got a system what we want, we got a system pumping speed is what we desire to have, given volume of the cavity to be vacuumed, and the pressure we are going to talk about, whatever the vacuum level that we are talking for this volume. If I know this is my general expression for dP by dt, and then one can get a system pumping speed, and then I have to decide what my pump speed should be for in order to get my SS for a given pre-requirement. So, it is a very general expression, and whatever you want to do with this now, you can do all the mathematical treatment to this. It is important to note that both Qi and SS are time dependent functions. So, my mass in leak throughput can change with time. It can change because gas in leak, because outgassing being dependent on time can change with time. Also, I can say my system pumping speed also could change with time. So, I can write Qi as some function of time, and SS also is some function of time. So, Qi is a f1 of t, SS is function f2 of t, basically just to show the time dependence of these two parameters. The equation can be integrated analytically or numerically if the transient variation of Qi and SS are known. If I know the function f1, all right, polynomial function or any other function, if I know the dependence of Qi on time, then I can put that function in this value and then integrate it to get. So, I should know basically some time dependent function of Qi. Similarly, I should know some time dependent function of SS, and I could then put these values, put these expressions analytically in this particular expression and then integrate it, and I can get the time to get some pressure from P1 to P2 or Pi to Pf. So, in this expression we say at steady state. So, ultimately when I run this vacuum system for a long time, let us say many hours, many days, depending on what is the volume we are talking about, what is the Qi we are talking about, and what is the pressure in our site is, what is my vacuum I am talking about. So, at steady state I will find that after a particular time there is no change in the value of pressure. I have reached some steady state value of the vacuum. In that case, I will say dP by dt equal to 0 at that steady state. So, at steady state or after a long time, the changes in pressure with time are negligibly small, and therefore, I can say mathematically my dP by dt equal to 0. And therefore, if I say dP by dt is equal to 0, I can say now I can have a relationship between Qi, and at that time I got the pressure as ultimate pressure. The pressure at the steady state is called as ultimate pressure Pu. So, this P value has become my Pu. It is the minimum possible pressure that can be achieved using a certain pump. Alright. So, whatever vacuum system I have used, whatever conductances I have used, after connecting those things, after running it for a long time, what pressure I have got is something like Pu. At that particular time, I got dP by dt equal to 0, and therefore, I got a pressure P as Pu, and this is the minimum possible pressure that I could get, or the minimum vacuum I could achieve using a certain pump. And therefore, I will get P is equal to Pu, and putting that value of P is equal to Pu in this, I will get a relationship now as Pu is equal to Qi upon Ss. Cancelling V out here, transposing on this side, I get ultimate pressure that can be obtained depends on Qi and system pumping speed. All right. So, Qi upon Ss is what minimum pressure I can achieve. If I know the value of Qi, I can put this and I can get my Pu value. If I know the system pumping speed, I can put it over here. I can know that my ultimate pressure, ultimate vacuum that is possible with such a mass flow in leak throughput and such a system pumping speed, I can get a value of Pu to be equal to this. It is important to note that for most of the pumps, Sp is constant in its operating pressure range. This is the fair assumption to say that if I got a particular pump, it has got its own pumping speed, and therefore, I will say that this pumping speed is constant right from when you keep the machine on and you fairly constant Sp over a period of time. All right. So, just as a fair assumption, I will say that for a given pump, pumping speed remains constant. So, that means Sp does not depend, it is not a function of time, Sp is constant throughout. Also, in a free molecular region, conductance C is also independent of pressure. So, if you see our expression, if my pressure is constant or if I am in free molecular region, C is, because C depends largely on the gas properties and C largely depends on the diameter and the lengths, the geometric parameters of that pipe which is going to be connecting the vacuum pump to the system. So, I can say again that conductance is also not a function of time. So, Sp is not a function of time, conductance is not a function of time, and therefore, in this relationship I can say 1 upon Ss is equal to 1 upon Sp plus 1 upon Co. We can say from here, if Sp and Co are a constant from the above expression, it is clear that Ss is also a constant or it is independent of pressure. I can see Ss can be a function of time depending on whether these two are a function of time. If I know the time variance, time dependence, I can put that in earlier expression, but because Sp and Co is fairly constant with time, they do not depend on time, I can say that Ss also can be considered as independent of time. That means, Ss is constant or it is independent of the pressure we are talking about. All right. So, we can have this assumption of having system pumping speed as constant. Therefore, for a constant Ss, the equation can be integrated with following limits now. So, if you go to earlier expression now, I can assume Ss to be constant and therefore, this is my expression. And we can now, if I want to find the time dependence on pressure, the only parameter which is depending on time will be now Qi, and therefore, my time will be at t is equal to 0, p is equal to p1, let us say to begin with, and at t is equal to some time, any time I am talking about Tp, my p is equal to p2. All right. So, this is my time limit I am talking about, where the pressure changes from p1 to p2, where the pressure decreases from p1 to p2, and if I have integration, therefore, I will have integration p1 to p2 vdp upon qi minus spp. You can see from here expression, and ultimately I will have on this side only dt parameter basically. So, 0 to Tp dt. All right, transposing dt on one side and getting all other expressions on the other side, we can get this particular expression. And then I can solving using a simple technique of solving an integration, I can put Qi minus SSP is equal to x and put a value of dP in terms of that, and then integrating and put some integration rules in place. What I get is minus V upon Ss log Qi minus SPP in the limits of P1 to P2 is equal to T in the limits of 0 to Tp. So, you just integrate based on available integration rules, what you can get is this expression. So, ultimately now put the value of P is equal to P2 and P1 in this expression, and I will get parameter, and we know that Pu is equal to Qi upon Ss. Putting the value of Pu also over there, replacing Qi as Pu into Ss in place, I get an expression like this. So, I get Tp is equal to now V upon Ss log P1 minus Pu upon P2 minus Pu. So, P1 in a given time Tp pressure decreases from P1 to P2, while my ultimate pressure value is Pu, which is equal to Qi upon Ss. I have got an expression now which talks about pump down time for a given volume to be vacuumed which SS as the pumping speed, which is constant, it does not change with time, while the pressure is during this T p time comes down from P 1 to P 2, while the ultimate pressure that could be achieved is going to be Q I upon S S. So, here is an expression I can now compute for a given S S, given volume, what is the pump down time, I can calculate for this expression, and this will be more clear when I do the tutorials ahead. All right. So, this is an expression for calculating of the pump down time. So, what a more important expression is 1 upon S S is equal to 1 upon S P plus 1 upon C O, that is the most important expression, and second is the expression for pump down time. With this background now, let us have a look at the tutorials and wherein you can understand all the basics more clearly. So, tutorial 1, we got two pipes of two different lengths and two different diameters in series. I think the lengths are same 400 millimeter, the diameters are 40 millimeters of one and 30 millimeter of one, and they are connected in series. And first problem is to calculate the overall conductance of the pipe assembly shown above. The pressure on the right end of the 40 millimeter tube is 150 MPa, 150 millipascal on this side, while the pressure on the left of the 30 millimeter pipe is 10 MPa. So, you can see that you got a 10 millipascal and 150 millipascal as two pressure. The ambient temperature is 300 Kelvin. All right. So, we got one pressure on this side, we got a one pressure on this side. The molecular weight and the viscosity of the air are given. All right. So, basically it is a calculation of the overall conductance of two different diameters pipes of two different lengths or same lengths. So, what you have apparatus is basically series combination of pipe. We know the working fluid, we know the temperature, we know dimensions 40 millimeter, 400 millimeter length, pipe 2 40 millimeter, 400 millimeter length. So, calculate the overall conductance CO. Calculation of flow regime first, in order to ensure what is in which flow regime I am, because depending on the flow regime I have to use the expressions for conductances. So, first is Knudsen number for pipe 1, we know D is equal to 0.04 meter, L is equal to 0.4 meter, T is equal to 300 Kelvin, R, mu and P is known to me. All right. So, the Knudsen number calculation is lambda by D, this is the expression. Put those values all over here and I get Knudsen number as equal to 1.132, which means I am in free molecule region because Knudsen number is more than 0.3. Similarly, I can do it for pipe 2 also. Similarly, calculating Knudsen number for pipe 2, what we have is Knudsen number for pipe 1 is 1.132 and Knudsen number for pipe 2 is 22.65, which is very, very high. We have not shown the calculations again, and therefore, you can see that Knudsen number has been directly calculated for the pipe 2. The Knudsen number for both the pipes are greater than 0.3. Therefore, the flow is free molecular throughout the series combination. That is first thing to be established, because that will give you now what expression for conductance to be used from the available table. The L by D ratios of each of these pipe being less than 30, these are classified as short pipe. So, we got an expression for short pipe free molecular flow, and the expression for the conductance could be used for these cases. So, conductance for pipe, which is D1 0.04, D2 is 0.04, L is 0.4, T is 300 Kelvin, and all these things are shown over here. We got a C1 for the conductance of the first pipe, put those values and get C1 is equal to 0.0173 meter cube per seconds. I am not going through all these parameters, just go bar. The expressions for D1, D2 in the short formula could be used as 0.04 straight away. Similarly, calculate conductance for pipe 2 now. We got again pipe 1 as C1 as 0.013 and pipe C2 we get 0.0079. The conductance for the pipe C2 is quite less as compared to what, because the diameters are different. The overall conductance now for a series combination is given as 1 upon C0 is equal to 1 upon C1 plus 1 upon C2, and therefore, I can calculate the overall conductance by this formula is going to be 0.00542. That means, I will get overall conductance now, which is less than any of these two. All right. So, which is less than 0.017, which is less than 0.007 also. So, as a result of this C1 and C2, I get overall conductance which is going to be less than even C1 and C2, and this is my final conductance now, which could be utilized to calculate the system pumping speed if I know what is the vacuum pumping speed is. So, this is my first tutorial to calculate the overall conductance for a series combination of a given pipe. Now, tutorial is, if this arrangement what we have just seen is connected to vacuum a system of 1 meter cube volume, and I got a vacuum pump at the other end over here. So, now I can see that I got an entire system with a known conductance which we have just calculated, with a vacuum pump on one side and system to be vacuum on the other side. So, my problem statement now, consider a vacuum system of 1 meter cube with an initial pressure of 1 atmosphere at 300 Kelvin. So, it is all at 1 atmosphere to begin with. It is connected to a vacuum pump via a connecting pipe as shown above. So, it is using the same system which we have just calculated the CO for. So, it is connected to a vacuum pump. The ultimate pressure of the system is 0.1 millipascal as shown over here. Determine the system pumping speed if the required vacuum in the cavity is 1 kilopascal in 1 hour. So, I know what is my PU, which is ultimate pressure. I know what my P1 is, which is 1 atmosphere. I know what my P2 is, which is 1 kilopascal, and I know what TP is, which is 1 hour. So, what is important to be known is what is my system pumping speed. What is the system pumping speed for a given pump and for given values of pressures. So, what is given to me? Vacuum pump system has been given to me. Working fluid is air at 1 atmosphere, vacuum is 1 kPa, vacuum requirement is 1 kPa, then temperature 300 Kelvin. I got a connecting pipe 440 millimeter, 400 millimeter, 40 millimeter, 400 millimeter, then time is 1 hour, volume is 1 meter cube, ultimate pressure is 0.1 millipascal. System pumping speed is SP. So, calculate the value of SS. So, what I know is all these parameters are known to me. V, P1 is 1.013, 1 atmosphere to begin with, to 10 to power 5 Pascal. P2 is 1000 Pascal, all right. Then Pu is ultimately what I have got is a 0.1 millipascal, which is 0.1 into 10 to the power minus 3 Pascal, and Tp is given as 1 hour, which is 3600 second. So, I know P1, P2, I know Pu. So, all the things in the formula is known to me. So, I got a formula which is SS is equal to V upon Tp log P1 minus Pu divided by P2 minus Pu. I know almost all the values and I can calculate what my SS is, and therefore, I can put the values over here and I can get my SS to be equal to 0.0012 meter cube per second. This is my system pumping speed is. So, if I know system pumping speed, if I know the conductances over here, I can now calculate my pumping speed or vacuum pump speed required for this particular operation, so that I can have Tp to be equal to 3600. So, from the earlier tutorial, we have understood that Knudsen number for pipe 1 is 1.132, Knudsen number for point 2 is 22.65, Knudsen number is more than 0.3 and the flow is free molecular region. This is what I know. Also, I know the conductance of these short pipes. I know conductance for pipe 1 is this, conductance for pipe 2 is this, as a result of which we have got overall conductance of CO as 0.00542 meter cube per second. So, if I were to connect all these parameters together, I got a relationship of calculating my SP. What is required for that is to know what is my overall conductance and is to know what my system pumping speed. I know both these parameters, and therefore, I got expression now 1 upon SS is equal to 1 upon SP plus 1 upon C0, and therefore, from there I get 1 upon SP is equal to 1 upon SS minus 1 upon C0, all right. So, put the value of system pumping speed, put the value of conductance, and I will get now what my SP should be, what is my pumping speed should be. So, 1 upon SP is equal to 1 upon 0.0012 minus 1 upon 0.00542. Putting this value, I get my pump speed to be equal to 0.00154 meter cube per second, all right. So, SP is going to be 0.00154. So, this is my pumping speed, and therefore, converting that into liter per minute is SP is 92.4 liter per minute. So, I should choose such a pump now, which is having a pumping speed around this approximately, ideally, theoretically we are talking about. So, actually I should collect all the outgassing in a connections here, also here, and therefore, I should have a pump which has got a pumping speed more than this, at least 50% more than this, and therefore, this will give me first calculation to understand for a given pump. If I want to do vacuuming from a given P1 to P2 in 1 hour, with this such a connections over here, I should have a pump of capacity 92.4 liter per minute. And this is the way we do this initial calculations and then put all the reality factors in this in order to decide which pump I should buy. With this, we got a summary of the lecture. Correlations for conductance for some commonly used pipes and pipe joints are given. So, we got a short pipe, long pipe, we got a elbow, and we know the conductances expressions for this. If you want to know more such expressions, you will have to refer to some vacuum books where you can get some intricately shaped T points and things like that, where you can calculate the conductance for such a joints, such joint and such pipes also. We know that the pumping speed is given by SP, which is equal to Q upon Pi, and we know that the system P is nothing but SS, which is equal to Q upon P, where P is my pressure in the system, while Pi is the pressure near the vacuum pump. We also know the relationship between SS and SP, and 1 upon SS is equal to 1 upon SP plus 1 upon C0, from where we understood that maximum SS can be equal to SP if C0 is infinite. If conductance is infinite, SS can maximum be equal to SP, but SS can never be more than SP. Alright, so this is the maximum relationship, that SS can be equal to pumping speed only. SP depends on a vacuum pump, and therefore, in order to maximize SS, CO should be maximum. So, my conductance or the connection from the pump to the vacuum system has to be of a bigger diameter and minimum length. If required, this pump should be directly mounted on the system to be vacuumed. There is no point in having a low conductance in this. So, if I got a very high pumping speed, there is no point in decreasing pumping speed by connecting it to some capillary tube or something like that. I should ensure that this pump directly sits on a system to be vacuumed, so that my CO is actually close to infinite value, and that is the way in practice the decisions will be done. For constant SS, we have an expression as Tp is equal to V upon SS log P1 minus Pu divided by P2 minus Pu, and this is the expression which we use to calculate the pump down time for a given volume V to be vacuumed from P1 to P2. Thank you very much.